Good morning, dear Spark Summit participant. I hope you have had a nice day so far, and our day would be even nicer and smarter after these data science sessions. Today I'm going to talk about using publication metadata to identify mentor-mentee relationships via Spark. Here is an outline of my talk. Firstly, I will introduce the Elsevier and Scopus data which we use. Then I will explain how we will build our mentorship model within a graph framework, how we train and validate the model. And finally, I will present some results from the recent libraries that we developed for graph visualization in Spark. So I'm from Elsevier. Elsevier is the leading publisher of scientific materials and information technology. We are privileged to have about 25% of scientific publications. If you are a researcher in a university, you perhaps have already used our website or our journals without maybe noting that. Elsevier publishes about 400,000 articles per year in about 2,500 journals. Some of them you may know, like Cell, Lancet, Current Opinions, Artificial Intelligence, and so on. This publication can be accessed individually via the journal website or via our main platform, Science Direct, which has about 1 billion full text download per year. Elsevier publishes the scientific articles and books and conference proceeding as well, but is also a primary curator of scientific information, meaning that, for example, the publication data, the scientific evaluation of different research institutes, persons, organizations, and countries in products like Scopus, Cyval, and Pure. May I ask how many people have actually used Science Direct? Great. So this is something that you will see in Science Direct if you do a research or search, and you can actually see in this corner the Spark, Apache Spark publication count since 2013. It has doubled or tripled every year, and 2016 is not yet over. So a growing research area. My main work is based on Scopus data. Scopus is the biggest abstract and citation database in the world. It covers about 65 million research articles going back to 1823. It includes data such as author's title, where it was published, what was the affiliation, what articles were cited, what are the keywords, what are the subject areas, and so on. This is the Scopus GUI if you go to our platform to use it. And may I again ask how many people have used Scopus? Okay, much fewer. Okay, so let's look at the content within Scopus. So Elsevier is a leading publisher, but we only publish about 25% of scientific materials. So we curate a lot of data, mainly metadata, not the full text from other publishers, and we incorporate all of those in Scopus. You can see it covers about 65 million scientific articles, also about 27 million patents from 5 different offices. It includes articles in the press from different countries, from different publications, and so on, and also conferences. This product can be used as a search for data science, but it can also be used as an API if you are doing research about research productions, about publications. For example, if you want to compare different organizations. In a very simple way, you may think that Scopus is similar to, let's say, Google Scholar or Web of Science, but there is a big difference, and the difference is that practically everything in Scopus is disambiguated. So if there is a citation, if there is an author, if there is an affiliations, we can track those over time, over different organizations and over different hierarchies. So that's what makes this unique. Because otherwise, for example, if you go to Google Scholar, you can search for my name and you will see all the publication of Reza Karimi. You cannot see which one was actually me unless I have created a Google profile. But in Scopus, we have author profile. We know where they published, when they published, with whom they published, in which organization, under which affiliation, and so on. So you can look at that information. For example, when you click on an author, and then look at their publication over time, their co-author, perform some analysis there. Or you can look at an organization, which we call affiliation, look at the university chain level, university levels, department level, dean levels, labs, and so on. We have about 65 million articles, about 12 million distinct authors here, the main authors, and about 10 million affiliations, which is actually 7,000 primary affiliation and a lot of hierarchy under that. So to give you an insight how this data is disambiguated, which is actually my main work in Elsevier, we have an algorithmic disambiguation. All the published document and incoming documents are profiled, meaning that we cluster the author's affiliation, we perform the duplications, and then we create profile for author, institute, citations, and so on. There is firstly an algorithmic way, and then there is a feedback in the tool. You can claim your publication in a Scopus or for your organizations, and then we verify it with our team, customer service teams, and we apply those corrections, and that will impact our algorithms. We also import a lot of author profile online, for example, from ORCID. So we can match the documents against that as well. We have other services like Scival and Pure. Scival is for, let's say, research organization, performance evaluation, and Pure is more like a country-level research evaluation. We also use the feedback from that, and sometimes the government or institute reach to us and tell us that this is our publications and this is our authors, so we import those data. So this is relatively a very precise author disambiguation, and that's why I can actually perform mentor-mentee relationships detection. And this is my final slide about Scopus data, the data I use. You can see where it's being used. A lot of big industries like Siemens or Volkswagen use it. The funding agencies like European Research Councils or NSF use it. All the ranking institute for universities use it, and also big universities. So it's quite a good data, high quality data. Okay, I hope by now you know why we use this data and perhaps why we trust it. But let's start in the ML modeling, which is far more exciting for most of the audience here. So when we look at the publication, the thing that we can extract is some authorship graph like here. So we have one author, let's say, model them as vertices, and then we have edges between them, like this document, that document, and so on. To give you statistics about this data, as I said, 65 million document, about 33 or 34 million authors, some of them dummy authors, which will result in 4.6 billion co-authorship graphs. So if you want to imagine this network or this graph, it has about 33 million authors, vertices, and about 4.6 billion edges, which for a lot of you may not be actually a big number, and I agree. The trick and the challenge here is that each edge is of distinct type. So each edge is a document which represents a lot of information. Yes, author I and J published together in this document, but there is a lot of context in this information. And even if we consolidate those information to author pairs in co-publication, we have about 382 million author pairs. And we also specifically look at the correspondence authorship. The reason is that in a lot of fields and a lot of countries, the correspondence author gives us a very good clue about who is the principal investigator and who is likely to be the principal mentor in the project. Okay, this is the co-authorship graphs. Now I'm going to formally define the problem. So the problem is find the most likely mentor among co-authors. This is already a little simplified because someone may not publish with someone. Or we have edge cases that the actual advisor is the co-author of the co-author, but that's very exhaustive to calculate because if we look at a lot of people, they have about 1,000 co-authors. And then you look at the co-author of co-authors, we are talking about the quarter of millions. So we simplify the problem to find the mentor among co-authors. And now let's find a solution. So I'm going to reverse engineer this definition to come with a solution. First, we have the most likely. It's very easy for a data scientist. We say, let's form it as a ranking problem. And then being mentor, it's also looks easy. Let's make it a classification problem. And now comes the difficult part. We have a classification problem, but what is the input for that classification problem? And what is the training data for that classification problem as well? So ideally, if I want to find someone's mentor, I would like to look at all its co-author at the same time, but that's not very scalable, and that's not very straightforward. So we instead opt a pairwise model, meaning that I create a model which will give me a score, a classification, a score, a probability, that this guy is my mentor. I apply that model to all my co-authorships, and after that, I rank the co-authors for being a mentor, and I find it. That's one simplification to define the classification input, so we are comparing two vertices only at a time. And the next simplification is that we aggregate all the data, all the edge between two vertices, like document A, B, C, D, E, F, and so on, into some aggregated graph, and that is the beginning of the solution. Now comes the next part. Find the data to train this model. And it's always like eggs and chicken. If you have good data, you can build good model. With good model, you can produce more data. So where to start? And this is actually very difficult. When I started, I thought I know my advisor, and I know he's a student. But then I looked at his co-authors, and he's a student since the beginning of his professorship, 1980. It's like 1,000 students. It's just very hard. He doesn't even remember the name of many of his mentee. So we needed a better way to come up with a solution. So here is what we started. We started with a simple heuristic model. I disclosed the result of that with 25 close friends and colleagues. And then we made a small adjustment to that model, heuristic model, and went for crowdsourcing. The good thing about this heuristic model is that they are simple. You can build them. You can adjust them in a way that you adjust your thought if you had the same situations. And that gives us a good starting point. We tell people, is this guy your mentor or not? And that gives us positive and negative data to actually build the next ML model. To give you an insight, the first heuristic model is about 60% accurate. The next heuristic models, we included some continent and country variation, 70% models. We applied crowdsourcing, consistent accuracy as we expected. And here we can get 80%, maybe 90% here, but we haven't yet done any online evaluation of this final result. The problem with heuristic model is that you can build a lot of features there. I know if I have some published more with someone, he's more likely to be my mentor. If someone has published also more in my early career years, he's more likely to be my mentor. But we cannot really properly model the interaction between variables or the proper weight, because what if someone has published less but has published more in early career years? Who is the likely mentor? So that's why we just built some simple model so it will not be overfit. We really didn't tune it. We sent it with email campaign for verifications, and then when we collected data, we started to actual ML training. Okay, so that was a bit of theory and the background in the modeling systems. Now I'm going to explain the Spark pipeline. So we have about a few terabytes of data in XML formats in S3 in AWS. We run those data through compute optimized node and store the result in JSONs, which becomes about a few hundred gigabytes. And after that process is over, everything can be followed with memory optimized nodes. And And then we store data, we transform data into Parquet columnar data. You can see it here. And that's about a 10 gigabytes, something order of that size. So each steps reformatting makes one order of magnitude reduction in data size. And after this point, we expand the data in two ways, like nodal data and edge data. And for each data, we have a lot of features which we compute with, let's say, with separate jobs or a series of jobs. So, like, for example, you calculate edge index for someone. You calculate the number of publications together. You calculate the statistics on publication and so on. One thing to notice is that there is a lot of variation in different fields and in different countries. For example, we have a publication from CERN, which have about 4,000 authors, which will result in, let's say, about 6 million co-authorship pairs. So with those things in mind, it becomes very important to apply a weighted aggregation to our data. And you can see that, for example, for aggregating data into the nodes, we apply a 1 over n authorships and a similar thing, a 1 over n multiplied by n minus 1, which is the number of the pairs for co-authorship in articles to weight the result. So if I have published with less authors, with less co-author in a paper, that tells something more about me than if with more. And during aggregation, we have to also deal with a lot of non-numerical features, for example, affiliation, countries, subject areas, and so on. One way we deal with that to simplify the problem is we just take the most common value, and at times we also look at the frequency of the most common value. Another approach for some other variable like the subject content of someone is that we calculate subject content representation for someone, let's say, how many papers they have published in which journals. And then from there, we calculate this for two vertices, and then we calculate a cosine or overlap share to just come up with a similarity in the edge. Here is a simple representation of the problem. So this was the co-authorship graphs, and this is corresponding authorship graphs. A lot less connectivity here. Because for a paper with n authors, we have about n squared co-authorship, and we have about n minus 1 corresponding authorships. We merge this data together, and then we have these different edge types, and that's the beginning of our models. To give you a bit more insight about the features, because they are really important, we have number as well as weighted sum of authorships, co-authorship, and corresponding authorships. A lot of these features are calculated in dual ways, meaning that we have calculated that for the node, but something similar also for the edge. For example, we look at the time series. When someone reaches the first 3, 5, or 10 publication count, when they reach it, and when perhaps they together reach that publication count. Other feature is like citation metrics, number of co-authors, and also from the From the graph perspective, something which is interesting is that we simplify the problem to a pairwise model, which is good, but a pairwise model, very simple pairwise model, discards a lot of information. So by aggregating data into the nodes, statistics into the nodes, we can employ some global information. Besides that, we also incorporate some things like page ranks and other graph metrics, importance metrics, into the node, which will tell us something more of a global relationships or importance of the node. Okay, no Spark talk without a little Spark code. So that's the final application. You can see it here. Just define a graph with a graph frame or not, with the vertices and edge, which are a lot of data put together, and then just find a simple path. This is for pairwise model. And then apply that path data to a mentorship score. This can be heuristic or this can be ML model, and that's it. After that, you just rank these mentorship scores and you keep the rank one on its mentor-mentee graph. One thing which I also wanted to mention was that I found this notion of the graph frame very useful, because before that I had to really, let's say, join two data to my edge data and then change names or make it key value, and now this makes it very convenient format. Okay, after we compile, we calculate the pairwise scores and we pick up the first mentor, we have a bit of problem to solve. And that's the fact that the pairwise model, they are very local. They cannot employ global constraint. And one important constraint is that I cannot be the mentor or mentee of the same person. In fact, we cannot have a loop of mentor-mentee. So what we can do to resolve that is essentially we look for loops of L2. We break the loop by the weakest length, replace the next candidate, and then go through this a few times. This can be done up to, let's say, L equal to 4 easily. But beyond that, it becomes very complex. So we also apply it for a subgraph at the end, for example, if you want to show the result for a specific item. We also validated this result via email campaign. We sent email, and we had 4 options. We asked people to specifically click on a link and then submit. And then here is our result. We had about 10,000 audience recipients, about 4,300 opened their email, about 1,700 clicked on the link, and about 413 actually submitted a choice. Here is the choice distribution here. We had primary advisor choice, one of the primary advisors, a non-primary advisor, but still an advisor, and a non-advisor. And in summary, we had about 59% accuracy in correct primary advisor and about 70% accuracy in identifying an advisor. The good thing about this, having a single primary advisor, is that this gives us one positive example, training example, and a lot of negative examples. This gives us one positive examples when we look at all the co-authors, and this gives us maybe nothing or maybe neutral option, and this gives us one negative example. So after this practice of this first email campaign, now we have a few thousand training data that we can use to improve our model. We also look at the click versus submit, and we found that about 94% of people actually submitted the same choice as the choice they click on the email, which is a good thing for us because it tells us that maybe we can also use this for training. The output of this model is to something like this, academic tree, and these academic trees are important because we can use them for people or article recommendation on our platforms like Mendeley, but they are also very important to identify the conflict of interest, for example, among a funding panelist or among reviewers for an article. The good thing about this mentorship graph is they are relatively very simple because they have low connectivity, meaning that each person has only one mentor and there is a limited time. So if you start from a node like this and go all the directions down, the graph will be over very soon. And interestingly, you can easily cache this graph into the memory of a Spark and then interactively work with it or even build a simple backend application for visualization, which I wanted to do that here, but then there come a problem of privacy of people or showing this result, so we had to blur this result. So instead, I'm going to conclude these mentor-mentee detections here, but also show you some other visualization from the libraries we developed for graph visualization. So for the graph visualization in Spark, we have to take two things into considerations. We want a subgraph creation, which can be very important, like how you filter a graph around a person or a node or around the global. The global filter is easy, but to come up with a subgraph within that, it's a bit harder. And then a bit of visualization library to apply those things. And here I use D3 JavaScript and display HTML to create this visualization libraries. The code that you can use, as you can see here, is quite simple. Literally, you just say, filter your graph the way you want, and then this link scale calculates the proper scale for visualization. And then you can say, give it this edge and vertices. You say what to group the nodes and edge and what will determine their sizes. And that's it. And then you get your visualization. Something like this. This is the top 250 global NonSelf citation between institute. You can see, for example, American Institute. You can see MIT, Harvard, Stanford here, all this Chinese institute, and you can also see Australian universities, UK universities, and so on. The color code shows also the delay between publication and citations, and so on. This is also another same graph, but in the computer science domain, which I thought is interesting for this audience, you can see that a lot of people are following Microsoft publication, and actually not so much from Google and Yahoo, which I think it's because they're not publishing so much or they're not very open. And finally, for those graph visualization, it's important to have modules that look locally. For example, this is the citation network for MIT, all the edges that are going or beginning from MIT. And this is the secondary citation network for MIT, like all the important citers within the distance of to MIT. And that's the conclusion. I mean, that's the end of my slides. Any questions?